Welcome to class today. I would like to start by having you try these startup problems dealing with compound interest and also finding, in this case, what's called terminal velocity. So try these problems and then we'll take a look at the way that you should have answered them. Okay, on the first one, you're asked to find compounded continuously. You've got 5 is going to be your t, this is going to be your principal, and then 0.08 is going to be your rate of interest. So when you look at how to put this in, this is the formula for compound interest that's compounded continuously. So I've got our principal, our rate, and our time, and put that in, and you get this as your answer. For the second one, a skydiver jumps from a reasonable height above the ground. The air resistance she experiences is proportional to her velocity, and the constant of proportionality is 0.25. It can be shown that the downward velocity of the skydiver at time t is given by this equation, where t is measured in seconds and v of t is measured in feet per second. Find the initial velocity of the skydiver. Well, initial velocity is always when t equals 0. So we're just going to go and plug in t equals 0 into this equation. So when we plug 0 in for that, we actually get 0 out from that because e to the 0 is 1. So 1 minus 1 is 0, and 160 times 0 is going to be 0. Okay, the second part, find the velocity after 5 seconds and after 20 seconds. So for those, you're just literally going to plug in 5 for the t and then plug in 20, and you get these two answers for that. And then finally, the maximum velocity of a falling object with wind resistance is its terminal velocity. So we want to look at the graph and find the terminal velocity. Basically, that's that value we looked at last class where it kind of levels off on the graph. So if you're looking at the graph, you'll see that it levels off about 160. So 160 feet per second would be that maximum velocity that it, or the terminal velocity that it levels off at. Okay, today we're going to be introduced to logarithmic functions. So I'm going to take a little bit of time to kind of look at the graph and the characteristics of the graph of the logarithmic functions, and then look at simplifying logarithmic expressions. So first of all, to compare an exponential and a logarithmic function, we've been talking about exponential functions. So they're of this form a to the x. They have a horizontal asymptote. That would be this blue graph. They have a horizontal asymptote at y equals 0. They have no vertical asymptote. The domain of exponential functions is all real numbers, and the range is going to be from 0 to infinity. It has a y-intercept at 1. So what happens is a logarithmic function is the inverse to an exponential function. So an inverse is a reflection in the line y equals x. So this is the line y equals x. So if we took and reflected the blue graph over, then you're going to see this red graph. And this, it didn't show up very well on the graph itself, but it actually comes down and gets closer and closer to this. So a logarithmic function actually has a vertical asymptote at 0. It does not have a horizontal asymptote. So what you'll see is because these are inverses of each other, we get a lot of things that are switched. So here we had a horizontal asymptote at 0, but this one has a vertical asymptote at 0. This one had no vertical asymptotes. This one has no horizontal asymptote. So it's just like they switch. Same thing is true with the domain and the range because they're basically switching their x's and y's. If you remember, that's what we did when we found an inverse, was switch the x's and the y's. So in switching the x's and the y's to get the inverse, here the domain was all real numbers. So on this one, the range is all real numbers. Here the range was from 0 to infinity. Here the domain is from 0 to infinity. So these are going to switch. Sorry that the pen's malfunctioning. Switch here as well. This one had an y-intercept of 1. This one's going to have an x-intercept of 1. So you see that they interchange on a lot of different in a lot of different ways. So this is read the log base a of x. So in looking at this original exponential function, we know that it has an inverse because it would pass the horizontal line test, and that inverse is the logarithm. So in order for them to be inverses of each other, this base and this base do have to match. So like if I had 2 to the x and log base 2 to the x, those would be inverses of each other. If I had 3 to the x and log base 2 to the x, those are not going to be inverses of each other because their bases don't match up. So the bases do need to match up for them to be inverses of each other. Okay, so we just said that the exponential function does have an inverse because it is 1 to 1. It passes the horizontal line test. Okay, so looking at this, we have a base here of a, and we have, and so what this is this is essentially, this log base a of x is essentially the exponent here. What I always tell people is this is logarithmic form, and this is exponential form. So you're going to go back and forth between the two, and I have a slide that kind of shows you how to do that. With logarithmic form, you start here with the base. Again, sorry that the pen is not cooperating too well. Start with the base. I'm going to circle around over here, and that's going to be my exponent. And then I'm going to come back and set it equal to x. So I'm going to start with the a, circle around to the exponent, and then it's going to equal the x. So just work in a circle there. When we go to put this in logarithmic form, okay, the a is my base. So I'm going to have to put my exponent over here on the other side. So the exponent's going to go over here, and then the x goes here. I think it's a little harder to go to exponential, from exponential to logarithmic, but it's just kind of undoing the same thing. You can always go in that same circle and make sure it gives you back what you started with. Okay, so these I would like for us to put in exponential form, and I'm going to go through these. If you feel comfortable and want to try them on your own, then that's fine too. Just pause it and try these. If not, then kind of follow along. So exponential form on this one, we're going to start with a base of 10. So start here. We're going to raise it to this power, to the 5th power, and then we're going to set it equal to the 100,000. So this would be its exponential form. Okay, on the next one, we'll start with a base of 2. We're going to raise it to the 3rd power, and we're going to set it equal to 8. Again, working in this circle. The next one, we start with a base of 2. We're going to raise it to the -3 power, and then we're going to set that equal to 1/8. And the last one, we're going to start with the 5th, with 5 for the base, raise it to the R, set it equal to S. Okay, we're going to use some of these to evaluate logarithms. And so one way of doing this is putting these in exponential form in order to evaluate them. So we're going to start here with 10 to the x equals 1,000. So what I want to do is I want to try to rewrite this number in terms of this base. So hopefully you remember that 10 to the 3rd power is 1,000. And then once my bases are alike, I can say that x is going to be 3. On this one, I'm going to have 2 to the x equals 32, putting it in exponential form. Then from here, I'm going to rewrite 32 as 2 to the 5th power. And so x is going to be 5. This one, I'm going to have 10 to the x equals 1/10. This one's a little bit trickier. 1/10, I'm going to come over here to the side, is the same thing as 1/10. And that's also the same thing as 10 to the -1. So what I'm going to have here is 10 to the x equals 10 to the -1. So x is going to be -1. This one, I've got 16 to the x equals 4. Okay, in the place of 16, since this is my smaller base, I'm going to rewrite the 16 as 4 to the 2nd. Okay, so I'm going to have 4. When I raise it to a power, I multiply my exponents. So I'm going to have 2x equals 1, so x is going to be 1/2. And then here I'm going to have 5 to the x equals 1/25. This is the same thing as 1/5 to the second. So 5 to the x equals 5 to the -2. So x is going to be -2. Okay, one of the properties from inverses called the inverse function property tells us that if we compose two functions together, if we have f of f inverse of x, then that's all going to equal x. And if we composed it in the opposite order, then that's also going to equal x. So by knowing that a of x and log base a of x are inverses of each other, then we know that if we compose them in either order, that also equals x. So essentially, as long as this base and this base match up, all that cancels and we're just left with the x. Same thing here, as long as this base and this base match, then all that cancels and we're just left with the x. Okay, so we get a few properties from that. The first property is the log of 1, regardless of what the base is going to be 0. The reason for that is if we look at the exponential form of that, a to the 0 is 1. Anything to the 0 power is 1, and therefore we get this property from that. Here, as long as this a and this a match up, then we get all that to cancel, and we're just left with the 1 there. Same thing here, if those two bases match up, we're left with the x. And then again, if this base and this base match, we're left with just the x. Okay, we have what's called a common log, and the common log is the key that you're going to see on your calculator where you see the log key, which is to the left of the number 7. That's your common log, and the common log has an understood base of 10. So anytime you see it written like this, it has an understood 10 as a base there. It's just the common log is so common that we don't write the 10 every time we write it. So if it's not 10, we write that base. If it is 10, we don't write the base. Okay, so here's a few properties. If you feel comfortable and want to try these, then go ahead, pause it, try it, and check your answers. If not, then stay with me and I'm going to go through these. Okay, the first one here, our bases match up. So this is just going to be 3. This one, I'm going to need to rewrite that. 64 is 2 to the 6th power. So then the bases match, and I'm just left with 6. Here I'm going to rewrite it as 2 to the -1 power. So these twos match. So I'm left with -1 as my answer. This one is a common log because it has an understood base of 10. So those bases match and I'm left with 4. Here the log of 1 is 0 regardless of the base. Here I've got this base and this base matching. So I'm left with 6 as my answer. Here this base and this base match. So I'm left with x minus 3 as my answer. And here, this one has an understood base of 10. And so this base and this base match, and we're left with 5 as our answer. Okay, we can do translations with logarithms as well. So I've got a couple here, but before we take a look at those, I want to use Desmos and kind of demonstrate this for just a minute. Okay, so what you see is a logarithm, a common log. I'm just going to work with common logs just because all the others are going to work the same with this. So if we look at different types of shifts, if we do log of x, and we do a vertical shift of up 3, then you can see that the whole graph just slides up 3. If I wanted to look at -2, then you can see that is going to shift it down 2. If I want to do a horizontal shift, the horizontal shifts are going to take place inside of this parenthesis. So if I do a 3, it's going to shift it to the right 3. And if I were to do a plus 4, it's going to shift it, sorry, plus 4, it's going to shift it to the left 4. So you can see that the shifts are going to work the same with the translations just as they have before. One thing to keep in mind is the vertical asymptote is going to shift along with the log graph. So where the normal or the original graph had a vertical asymptote at 0, then when it shifts, that vertical asymptote is going to be over here at -4 and so forth. So as far as the domain goes, last time when we talked about exponential functions, we said that it really didn't matter when we shifted left and right, but the only thing that was going to matter was the up and down. So the range was going to be affected by the shifts. Here is the opposite of that. So if my domain is what's going to be affected by left and right shifts, but the vertical shifts are not going to affect the range for us because the range is going to continue to be all real numbers. Okay, so try these and determine what the translation is and what, as well as the domain, range, and asymptote. Okay, if you look at the first one here, this is actually going to be a vertical shift, so it's going to move it up 2 units. So we've got our basic logarithm graph, and it's going to be shifted up 2 units. So this is just kind of a thumbnail sketch of what we would expect here. Our original graph had a vertical asymptote here at 0, so shifting it up doesn't really change that, so it keeps the vertical asymptote at 0. The domain is still going to stay from 0 to infinity. The range would be from negative infinity to positive infinity. Down here, this is going to shift it right 3 units. So here's my regular graph with a vertical asymptote at 0. And then here is my shifted graph that has an asymptote at 3. So everything shifts right, including the asymptote. So the domain, instead of being from 0 to infinity, is now from 3 to infinity, but the range is going to stay the same at negative infinity to positive infinity. Okay, so I want to talk briefly about natural logarithms and some of their properties. So the natural log has special notation, just like we use the base of base e for that exponential function. The logarithm, instead of writing it as log with a base of e, we're going to write it as ln of x. So I do not want to see it written like this. That's inappropriate notation. So ln of x is what you want to replace this with anytime that you're using it. And it has its own key on your calculator. It's to the left of the number 4. So it's going to be the ln key. And basically, that is called the natural logarithm, and we use that a lot. It's one of those naturally occurring logarithms that we use quite a bit in calculations. You can see they are inverses of each other, and so they're going to be reflections in this line, y equals x. Okay, so these are just special cases of the logarithms that we've already looked at. So the ln of 1 is 0 because we know that the log of 1 is 0 regardless of the base. So that's true for ln as well. The natural log of e to the first power, remember natural log has a base of e, so anytime you see ln and e together, they're going to cancel each other out, and you're going to be left with just the 1 there. Same thing here, these have the same base, so they cancel and you're left with x. And also here they cancel and you're left with x. And the reason they're canceling is because of that inverse property that says if you compose 2 inverses together, then they're going to cancel and leave you with just the x. Okay, so here's a couple for us to look at. The first one, ln of e to the 8th, those two cancel and we get 8. I would encourage you not to necessarily put these in your calculator unless you can't figure them out otherwise, because you really need to learn these properties and not just rely on your calculator for those, especially if you're someone that's planning to go into calculus next semester. Okay, this one, I'm going to do a rewrite of it and bring this up because even though they're together here, they need to be side by side before we get that cancellation. So this will be to the -2 power, and now I can cancel those and just say I have -2 as my answer. Now this one is not one we can match up bases. So I actually am going to give just a decimal approximation for that. So if I put this in my calculator, I'll get 1.609. Just be cautious of how many decimal places your calculator is telling you to give that to round to. Okay, so here's a few to practice with. Again, if you feel comfortable, go ahead and try these and pause the video. If not, then just stay with me and we'll look at these. Okay, the first one, the natural log of 1, the log of 1 is always 0 regardless of the base. Here, the natural log of -3, you cannot take the log of a negative number, so this one is going to be a does not exist. Here, the ln of e to the 4th, those cancel, so that's going to be 4. These cancel, so that's going to be 5x. These cancel, and that's going to be 3. And these cancel, and that's going to be x squared minus 5x. Okay, so I have a few here where we're going to start solving some simple exponential and logarithmic equations, and generally that involves putting them into exponential form. So on this first one here, I'm going to start out and I'm going to do 4 to the 4th power, and I'm going to set that equal to x. So 4 to the 4th equals x. And so 4 to the 4th is 256, and so that's where I get this as my answer. Here, this has an understood base of e, so e to the 3rd equals x. This looks funny, like it doesn't look like it's an appropriate answer, but e to the 3rd is that 2.718 ... to the 3rd power. So that is just a number, so you are actually finished at that point with that. Here, the natural log and the e cancel, and you're just left with x is 2. Okay, this one is, we just need to solve for the x, so we're going to divide both sides by 3. One thing I want to point out is that this is not the same thing as this. So be really careful that you don't pull that 3 up with the 5, that you leave it completely dividing into this whole expression here. Okay, and then the last one, this has an understood base of e, so e to the -1 equals t plus 7. And that's just going from my base to my exponent around to this. So e to the -1, I'm going to subtract 7 from both sides to get t by itself. So e to the -1 minus 7 equals t. So that would be your answer. Doesn't look exactly like we would expect an answer to look, but that's what you want to give as your answer there. Okay, finding the domain on these is important. In the past, we've looked at different things that can cause domain restrictions. One was denominators, and the other was radicals. Now that we've looked at logarithms, we're going to learn that logs is the third type of restriction that we have to consider. So whatever we're taking the log of has to be positive. So I'm going to set this so that it is positive, greater than 0, and solve it. So basically that's where I get this as the domain. Okay, it has to be from 6 to infinity for the domain. This one's a little bit more complicated. ln is just a special case of logs, so we need, again, to make sure that this is positive. And in order to do that, we actually have to solve it as one of these inequalities where we have to factor and get our cut points. So our cut points, once we factor this, would be 2 and -2. And then when we put our test points in, we're going to see that it's a negative, a positive, and a negative. So we're interested in the positive part. And so that's going to be from -2 to 2. And if you think about it, if I were to plug in a number outside of this interval from -2 to 2, let's say I plugged in 3. That's going to be 4 minus 3 squared, so 4 minus 9. would be -5. I can't take the natural log of a negative number. And so I'm going to have to, I can clearly see that that should not be part of its domain. Even the number 2, if I did 4 minus 2 squared, that's going to be 0. I can't take the natural log of 0 either. And you can try this on your calculator. It's going to give you an error though. So if I take the natural log of 0, I get an error. And that's why I don't have brackets here, but instead I have parentheses. So just be really careful about making sure that whatever you're taking the log of is a positive quantity. Okay, that takes us to the end of this section. Let me know if you have any questions, and I hope you have a good day.